chapter in our book. We're journeying into the quantum mechanical model of the atom. We've got this delightful quote from Niels Bohr. Niels Bohr came up with one of the models of the atom. We'll talk about it briefly, his model. He said, anyone who is not shocked by quantum mechanics has not understood. There are some other really fun quotes about quantum mechanics from like the greatest minds in physics and chemistry. And they're basically just, yeah, I've got no clue what's going on. It's super confusing. And so that's cool because that means that what we're going into is really scary. It's really difficult. However, it's also cool because the greatest minds in physics and chemistry didn't really understand it completely. And so there's no pressure for us to think that we need to understand it completely. Lots of this is like, I'm just telling you stuff. I'm not 100% exactly sure what's going on behind the scenes. Nobody who teaches this is 100% exactly sure what's going on. So that takes some of the pressure off. So going back to the 20th century, beginning of the 20th century, the 1900s, it was believed that all physical phenomena, everything that happened out in nature, was deterministic. This is like if you've got a video of a baseball player throwing a baseball and you see the path the baseball is going on towards home plate, you could predict, okay, the baseball is heading right down the middle, the batter's starting to swing, you would either be able to know that they're going to hit it or they're going to miss it. And it's going to go right down the middle, it's a strike, or it's going somewhere else, it's a ball. That would be deterministic. Or like when you see, I feel like there's videos that start where it's like something bad is about to happen, like somebody's walking through a crosswalk and then there's a car that comes up and it pauses right before they get hit by the car. They're like, yep, that's me. You might be wondering how we found ourselves here, right? That's deterministic. You know that the car is about to hit the person, so you can tell they're probably going to get at least a little bit hurt. They're going to get bonked by the car at the very least. That's deterministic. Math is predictable. This is not true for all physical phenomena. So for subatomic particles, things are smaller than atoms. Smaller than atoms. The present condition, the state that we're in, does not determine the future. So you can't see like a subatomic car about to hit a subatomic person and know that that person is actually going to get hit. There's a reality in which the car goes past them. It doesn't hit them, it just like phases through them. Or now suddenly the car is further back from where it was before. If you shoot an electron down a path, you measure where it lands. A second electron shot down the same path under the same conditions will probably land in a different place. So this would be like if you have, an MLB pitcher throw 100 pitches and they all look like they're going right down the middle, and then like 50 of them are balls. Even though it's the same fastball right down the middle the whole time. When we're talking about quantum mechanics, the absolutely small is what we mean by quantum. The smallest quantity that you can measure is a quantum. That's sort of like, it's related to that. So it's the absolutely miniature small, like Quantumania, Ant-Man Quantumania, right? They went down into the super, super tiny little world. That's the quantum part here. Smallest, I don't know why I'm so bad at writing today, smallest amount would be a quantum. When you do not observe them, small particles like electrons can be in two different states at the same time, which is very fun. An unobserved radioactive nucleus can be simultaneously emitting a particle and not emitting a particle. You may have heard of Schrödinger's cat, which is coming up in a little bit. This is related to Schrödinger's cat. Electrons are really, really, really small. If you take a single speck of dust, a tiny little piece of dust, that piece of dust has more electrons than the number of people who have ever lived on Earth. It's got billions and billions and billions of electrons in it. And those electrons, their behavior determines how the atoms behave. Directly observing electrons in the atom is impossible. for many reasons. When you get down to this super, super small world, observing it changes its behavior. So if you observe an electron, then it will behave one way. If you don't observe it, it might behave two ways at the same time. If you observe a different part of it, it might be different from the way that you observed it previously. And there's an experiment where you shine a light on a path of electrons, and that is also shown to affect the electrons. So stuff, once you start to get really, really small, gets really, really weird. And the Schrodinger's cat experiment, there's some links here. I think they will break the recording if I try to click on them. That's typically what's happened in the past. But they're linked in the slides, so you can click on those from the slides and find them. You could also probably just Google Schrodinger's cat and minute physics or whatever this acronym is. And here we've got some quotes from great minds. Niels Bohr, anyone who is not shocked by quantum mechanics has not understood it. We saw that at the top of the lecture. Schrodinger, the guy that came up with the Schrodinger's cat experiment or thought experiment, said, I don't like it and I'm sorry I ever had anything to do with it. And Albert Einstein apparently attempted unsuccessfully to disprove quantum mechanics up until he died. So some of the great minds. Richard Feynman also has a quote, but I don't remember what it is off the top of my head. Richard Feynman's like one of the great physicists. Basically the idea, I think, behind Schrodinger's cat, his thought experiment, is you've got a box and there's a cat inside of it, and you put poison in the box. And until you open the box, you won't know whether the cat is dead or alive. The cat could have eaten the poison and died, but it could also have not eaten the poison and it could still be alive. So you don't know until you open the box and look at the cat that it's alive or dead. And up until that point, we could assume that it's both or either. And that's sort of like how the quantum world works. It's not dead or alive until you open the box. The quantum mechanical model does do some cool things for us. We will also not be exploring it in great depth because we don't have the tools to do that, which is cool for me because I don't want to do calculus. But it explains the manner in which our electrons exist and how they behave in atoms. And we're going to use the concepts from quantum mechanics to add some more theories on top of. For the most part, we're staying away from math. There's a little bit of math that we're doing, but this is a math-free zone. It's a low math environment. So if you're allergic to math, you should be fine. You don't have to take any allergy meds. It can help us explain some things like why some elements are metals and others are nonmetals. It can tell us why elements gain 1 electron when forming an anion versus some gain 2. It can tell us why some elements are very reactive and why others are practically or completely inert. And there's some other periodic table properties that we can learn from this. To start off, we need to talk about light. Light, as you may know, is a form of electromagnetic radiation. There's an electro part, there's a magnet part. So it's composed of 2 waves. Oscillating just means basically they're going up and down. And one is an electric field and one is for the magnetic field. Perpendicular means that they're at 90 degrees to each other. So for example, if we've got this one that's going up and down, not very good. We would have this other one that's coming in and out. I don't know if that comes across well, but the blue one would be flat, coming out of the board, into the board, out of the board, into the board. And they're oriented at 90 degrees to each other. So one's going up and the other's going side to side, happening at the same time. All electromagnetic waves, all light, moves through space at the same constant speed. In a vacuum, that speed is 3 times 10 to the 8 meters per second, which is the speed of light. converted to miles per second, that's 186,000 miles per second. So it can go around the Earth 7 times in 1 second. So it's really fast. That's assuming that it's in a vacuum. It slows down when it's in something else. Look at that. We've got it's even the same colors. We love to see it. So we've got our up and our down component, and we've got our in and our out component. You could also rotate that if you really wanted to. Energy is transmitted a lot faster by light versus sound. So if you've ever done track and field, or if you've ever watched track and field, usually if it's like the 100-meter dash, there's a guy at the finish line with a pistol, the little like smoke cap gun, and you watch for the smoke to come up, and then you start running, because if you wait for the sound to get to you, then you're delayed a little bit. So the light travels a lot faster than the sound. This is also why if you're watching lightning, if it's storming, you see the lightning, and then a couple seconds later you hear the lightning, you hear the thunder that's associated with the lightning. And it's so delayed because it's relatively very, very slow. When we're talking about waves, there are a couple of properties of waves. One of those properties is amplitude. Amplitude is basically the height of the wave. So the waves travel up and down, and there's a line along the middle that would be the average. For the line, that's like our reference point. So it's going to have a point where it goes up, and then it's going to go down the same distance, and then it'll go up, and then it'll go down. And the amplitude is related to the intensity. The larger the amplitude, the brighter the light, or the higher, the more energy that it's carrying. We also have the wavelength, which is the different distance between adjacent crests. And this uses the symbol lambda, which is also the symbol that Half-Life uses as its logo. This is typically defined as the distance from one crest to another. It could also be the distance from one trough to another. I think those would be identical. And wavelength determines the color of the light. A longer wavelength is going to look different from a shorter wavelength. It's going to look different from an even shorter wavelength when we're talking about visible light. So wavelength determines color, at least for visible light. It also determines what type of light it is if it's not in the visible spectrum. So we've split up the electromagnetic spectrum into different chunks, and those are based on how long is it between peaks on the wavelength, on the wave. The amplitude, the height of those waves, determines the brightness. So if you've got really small, short waves, those are going to be a dim light. If you've got really small waves, that's going to be a bright light. Related to wavelength is frequency. Frequency gets the Greek letter nu for its symbol. Usually when I draw nu, I give it this little front tail. And frequency is the number of waves that pass through a given point in a certain period of time. And usually that's per second. So how many of those waves can pass through a stationary point in 1 second is the frequency. The units for that are hertz. Hertz is equal to 1 over seconds, or per second. We also see hertz show up when we're talking about sound frequencies also use hertz because sound uses waves, and frequency and wavelength both have to do with waves. The total energy is proportional, so it scales to the amplitude of the waves and the frequency. So bigger / taller waves, we're talking about bigger amplitude. Have more energy. Faster / more frequent waves also have more energy. And there's a relationship between frequency and wavelength. Because all the waves are traveling at the same speed, they're traveling at the speed of light, the shorter the wavelength, shorter waves can pass through more frequently than longer waves. Do another bad job of drawing a wave, and then we'll try to draw one that's got a higher frequency. Ooh, it's so bad. But we get the idea, hopefully. So if both of these waves are traveling, if we see them traveling off to the right, this top one has longer wavelength. And because it's got a longer wavelength, it takes a longer amount of time for that wave to pass through a stationary point. The one on the bottom is shorter, and so it's going to be able to get more waves through the same point in time compared to the top one. Another way that we could think about this, the analogy that I used for my Chem 20 was vehicles. So if we've got people in vehicles, or if we're trying to get a bunch of people from point A to point B, if we put each person, one person, into a semi-truck with 2 trailers on it, that's going to be a really long vehicle. It's going to take a long time for us to get all the people in all those semi-trucks moving through a point, versus if we have them all in like motorcycles. If we've got them all in motorcycles, then we could fit probably like, I don't know, at least 8 or 9 motorcycles in the same space as a semi-truck. We'd be able to get them all from point A to point B a lot more quickly because they're packed together more closely. So our relationship here, frequency is equal to speed of light. Speed of light is a constant, divided by the wavelength. And those are units that we'll typically see. Sometimes we'll see wavelength expressed in something other than meters. We would want to convert it back to meters. As I mentioned previously, color, the color of the light is determined by its wavelength. Frequency and wavelength are related to each other, so frequency could also be used to determine color of light. I usually talk about it as wavelength, determining the color. White light, like we get from the sun or from some full spectrum light sources, is a mixture of all the colors of visible light. And so we've got this image of white light coming into a prism. Because of the way that the different wavelengths interact with the medium, it spreads out, it travels through the other side, and it spreads out even more, and then we've got something that looks like a Pink Floyd album cover. So that white light has a continuous range of all colors in it. And those colors, the mnemonic device that I've seen most frequently is ROY, G, BIV. Red, orange, yellow, green, blue, indigo, violet. And an important thing to know about light is that when light hits something, some of that light gets absorbed, usually. Some of that light gets reflected. And so in the case of this person using this laptop, their sweater, their top, appears red. That means it's reflecting red. The color that we're seeing is the color that's reflected. The color we see is what's reflected. And you can maybe do calculations to figure out the colors that are probably absorbed. What color are most plants? Green. Most plants are green. If you put a plant under a green light to try to give it food, because plants turn light into energy, if you put it under a green light, is that going to do anything for it? Is it going to be able to absorb that green light?
No.
No, why not? It's reflecting green light. So usually grow lights for plants are like red, or they might be some sort of like yellow, or there'll be a blue color. They're going to be something other than green, because green is what they reflect. If you give them full spectrum, that would also work. Do we have any questions so far? All right. A laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency of the light. We have an equation. It was nu frequency equals c over lambda. Does anyone remember what lambda is? Okay. Wavelength. Yeah, lambda is wavelength. So we've got lambda. What's c? The speed of light. In meters per second. So let's look at what happens if we put in the numbers as we were given them. We put in 515 nanometers. Are things going to cancel out nicely for us? Yeah, we would have meters that cancel, but we would still have this nano prefix, and so we want to convert that into meters first. Who remembers what the nano prefix means? It is 10 to the negative 9. So 1 nanometer equals 10 to the minus 9 meters. We're subbing in the number for the nano, so 10 to the minus 9 meters. One thing that we could do with this is just turn the nano here into 10 to the minus 9. That would get the job done, since we would put it into our calculator and it would figure out the rest for us. But let's not do that. We've got nanometers, 1 nanometer on the bottom, 10 to the minus 9 meters on the top. That'll convert us from nanometers to meters. So 515 times 10 to the minus 9. And very inconveniently, it's not quite small enough for the calculator to put it in scientific notation. I think it's times 10 to the minus 7, but I'll count it up real quick. Yeah, it's 7. So we're going to use that number instead. And then the meters will cancel out nicely. We'll be left with units of inverse seconds. So our units are 1/seconds. And we do, in fact, get 5.83 times 10 to the 14. We could also, if we wanted to, write it as hertz, Hz. Any questions about the math or the unit conversions? A bunch of different types of light on the electromagnetic spectrum. We are going to talk about some of them. So visible light is just a small fraction of the entire electromagnetic spectrum. That's all of the different wavelengths of light that you can have. Shorter wavelength or high frequency light has higher energy. Radio waves that we use for transmitting radio are the lowest energy. Cell phones and stuff also use radio waves. Gamma rays have the highest energy. If you have high energy electromagnetic radiation, that can potentially damage biological molecules. It has enough energy that when it hits your cells, when it hits your body, when it hits structures within your body, it can cause bonds to break. It can cause ions to form. Where there shouldn't be bonds that are broken, there shouldn't be ions that are formed. So things like ionizing radiation can give you cancer by messing up your body. They can also kill stuff. This is what our full electromagnetic spectrum looks like. We're not going to talk about a lot of the parts. If you'd like to learn more about all of the different parts of the electromagnetic spectrum, you're welcome to go watch my videos from, I think it's also chapter 7. Yeah, chapter 7 from Chem 20. I talk very briefly about radio, microwave, infrared, ultraviolet, X-rays, and gamma rays. We're going to basically just talk about the visible light part today. We'll mention some of the other ones a little bit. What do we notice about visible light as the way it's laid out here? What do we notice about the order? Is there something that we can think of that also has that same order? Where might we see it? A rainbow. Rainbow has the same order. Visible light is in rainbow order. Which is nice. When we see a rainbow, what's the top or biggest band of color? Red. Red's going to be the big band. And then inside that, we'll have the rest of the colors in their order. I'm missing one of the colors, but we'll get the idea anyway. So it looks something like this, just with no gaps between them. If we were to stretch these lines out that I drew, if we were to stretch these lines out and flatten them and make them straight, which of those would be the longest? Which color here has the longest path? It's the red. Red is the longest. And if we look at our wavelength, red is the longest. And it goes in rainbow order all the way down to the inside where we see our violet, and that's the shortest. I think that this is a neat way of remembering the order of relationship between wavelength. Frequency is the opposite, so violet is going to be the highest frequency, red is going to be the lowest frequency. It's the longer wave, takes more time for it to pass through a stationary point, so you're not going to be able to get as many through. This is our semi-truck. Violet would be our motorcycles. Another thing that I'd like to point out while we're here talking about the electromagnetic spectrum is red is on the long side. Red would be right here. We can see it, sort of. What's right next to red? Infrared. Infrared is right next to red. And on the opposite side of the spectrum, we've got violet, and what's right next to violet? Ultraviolet. Does anyone know how to shorten ultraviolet? Yeah, it's UV. Does anyone know what gives you sunburns and skin cancer? It's also UV, ultraviolet, is what gives you sunburns. That's why we wear sunscreen, hopefully, and sunglasses, hopefully, when we're out in the sun. UV is ultraviolet. That'll give you skin cancer. It'll give you... Infrared does not do that. Ultraviolet gives you skin cancer. And right next to that is violet. Violet's high energy. Red is next to infrared. Infrared is like one of the ways that we can do sort of see in the dark. Remote controls also do that. I think the Wii uses it for the tracking in the remote. And that will not give you skin cancer. So those are some things that I think are cool that I like to talk about every time we talk about the electromagnetic spectrum. You can use a prism to separate light by wavelength. It separates out into the rainbow colors like we'd expect. You can also use infrared light for thermal imaging. This is typically what's used for thermal imaging because everything that produces heat is also going to produce some amount of infrared light. And usually the way that it works is the color that we see is heat mapped. So red is going to be the hottest areas, blue is going to be the coldest areas, and it's all just relative to whatever the camera is set up as. You can also use high energy radiation to kill cancer cells, different types of high energy radiation for different types of cancer cells. But basically the idea is if they find a tumor in your body, they can do calculations to figure out what energy they need to give the light so that it'll dump all of its energy basically just at the tumor, and they'll hit you from different angles so that they're all hitting the same spot on the inside. It's sort of like a magnifying glass. They're all hitting the same spot on the inside, but from different angles so that they're not damaging the healthy tissue on the way in, or at least not too much. So that's one way that we can use it to our advantage in medicine. You can also get interference with waves. So when waves interact, wave interactions are called interference. And there are two types of interference. There's constructive interference, constructive like building up, like constructive criticism, feedback that helps you improve or become better, or construction, building stuff. Constructive interference is when the waves are in phase, in sync, paired up, on the same cycle, lots of different ways that we can talk about it. They interact so that they make a larger wave. So waves that are in phase, their peaks are at the same time, their troughs are at the same time, and when you add those waves together, the peaks get even peakier and the troughs get even troughier. Bigger peaks, lower troughs, the effects are adding up. Sound can also do constructive and destructive interference. So like if there's a bunch of people talking all at once, we get a bunch of waves that are in phase, some that are maybe out of phase, but most of them are going to be in phase, and the noise gets louder if there's like 15 people versus just 5 people talking. And then for destructive interference, when they're out of phase, when they're opposite cycles or out of sync, then the waves are going to interact so that they cancel each other out. So we've got our wave on top here is going up first, then down. Our wave on the bottom here is going down first, then up. And they're perfectly paired up, matching each other, but in the opposite direction. And because of their size and how they're lined up, it levels out, and so there would be no noise that gets through, or no light that gets through. Destructive interference is what active noise canceling headphones or earbuds or other devices do. They pick up the sound waves that are coming from outside. They figure out, okay, here's the wave that we're hearing, and then they put the opposite wave into your ears, and that cancels out the sound waves from the outside to varying degrees of effectiveness. That's like the general concept, is this destructive interference. So that's something that waves can do. They can stack, and they can be out of sync and destroy each other. They can also diffract. So diffraction is like bending, sort of like bending. When traveling waves encounter an obstacle and there's an opening that's the same size as the wavelength, they can bend around it. So they hit a little gap and then they bend out in all directions. Or they bend in one direction. Traveling particles do not diffract. They just keep moving in their path. So it's like throwing a baseball. If you throw a baseball through a tiny little hole, it just keeps traveling through the tiny little hole the same way that it's traveling. When you see Steph Curry or some other elite shooter hit a all-net three-pointer, it goes straight through. It doesn't like go through the rim and then veer left suddenly or veer back towards the shooter suddenly. It just goes straight through, because that would be particle behavior. Waves, on the other hand, if you were to basically do the equivalent of shooting a three-pointer, it goes through the hoop and then it spreads out in all directions. So waves can do funny things like that. And we can show this in a diagram. So we're showing wave diffraction on the top, we're showing particle behavior on the bottom. So each of these lines on the bottom is a particle. Let's put some arrows on there. So when the particles go through the slit, they just go through the split. If they don't go through the slit, they just hit the wall. The waves, on the other hand, we're seeing the crests of the wave. So this wave is coming out and going into the board, and it's traveling left to right. You could think of this as like big waves of water working their way towards the coast. And they hit this barrier with a slit, and now the waves are traveling sort of in all directions. So it hits this little split, and then it spreads out. Unfortunately, I don't have a demo for us for this. So that's what's happening with diffraction. And particles don't do that because they just keep traveling in the same line. The experiment that you can do with this is a two-slit experiment. So if you take a light source, light behaves as waves and particles. If you take two slits that are equal distances offset from the light source, the light is going to travel to both of those slits. It'll hit the slits and then it'll diffract. So we're sort of like making two little light sources at each of these points. And it'll spread out again. And then depending on where they're hitting on this film, they're either going to stack up constructively, this is the blue one. They have equal path lengths, and so those are going to be constructive interference. In this dark spots, this bottom slit is traveling slightly further from this top slit, and so they're actually out of sync. And so now it's destructive interference, and we would see a dark spot. And this happens in a repeating pattern over the course of the film. diffraction, this like little slit, is also how cameras work. And you can do, I'm forgetting the exact name of it, but there's a version of this that you can do basically where you just cover up, if you've got a window, you cover a whole window with like a couple layers of paper and you poke a little pinhole through it. When the light is coming through, if the circumstances are right, the light will diffract through that little pinhole and it'll project an image of the outside on the inside of your space. It's like something obscure, I don't remember the name. Somebody more artsy than me might. So that's a cool thing that we can do with light, and that's how we got cameras. It was also observed that many metals will emit electrons when a light shines on the surface. So if you shoot light at a metal surface, we've got our light, it's traveling, it hits the metal surface, it will eject electrons. Sometimes, not all the time, but it can eject electrons. And we call this the photoelectric effect. The photo part being photons or light, and the electric part being electric or electrons. We can maybe call it the light-making electrons or emitting electrons effect. And this has some cool applications. Classic wave theory attributed this effect to the light energy being transferred to the electrons. Under this theory, only the intensity of the light would affect the emission of the electrons. So if you had a really bright light, it wouldn't matter what color it is or what wavelength it is. As long as it's sufficiently bright, it should cause electrons to get ejected from the metal. And if there was a dim light, a low amplitude or low energy light, then there would be some lag time. Think of it like charging up. Before the electrons were emitted, because they would have to absorb enough energy. Then the electrons are like, I've got all this energy, I have to go somewhere. And then they get ejected from the metal. If you used a really bright light, they would just be constantly being ejected. High amplitude light. And here's a diagram of what that looks like. We've got a chamber that's mostly vacuum. We've got our metal. We shoot light at it. Electrons get ejected off of that metal surface. They hit the positive terminal of this little electrode. We've got a little battery. We can measure current showing that electrons are being ejected. This is basically just an electron measuring setup. So shooting light at the metal, the photoelectric effect causes electrons to be ejected, or is the observation of electrons being ejected, and then we measure it on this little current meter. When they did experiments, they observed what we're seeing here. So we've got a graph, we've got our frequency of light on the x-axis. So low frequency, these are going to be low energy waves, or long wavelength. And on the right side are going to be high energy waves. Short wavelength. On the y-axis, we've got rate of electron ejection. And we've got two different lines that we're graphing here. We've got a low intensity light, we've got a high intensity light. Both of them have a 0 for their rate of electron ejection. So both of them cause 0 electrons. No electrons are being released at a given frequency. what we expected to see was that high intensity light would produce more electrons. Low intensity light, our red line, even if it's at this low frequency, that it would take some time, and then eventually the energy builds up, and then an electron's emitted, the energy builds up, an electron's emitted, the energy is built up, and then the electrons are emitted. And that's not what we see. We see that there's this threshold frequency of light. Once you hit this frequency, then electrons are ejected. And for lower intensity light, there's fewer electrons being ejected than for higher intensity light. So there is an effect of the intensity, but it only happens after a certain frequency. So there's a threshold frequency. That's this dotted line that I drew in here. And you have to be past that for any electrons to be emitted. And then once you're past that, once you've got more energy than that, once you've got a shorter wavelength than that, then light or electrons are emitted even for low intensity and more for high intensity. Einstein's explanation was that the light energy was delivered in packets. And a packet of light is sometimes called a quantum, the smallest amount, or more likely one that you've heard of, photon. Our photon is a single piece of light, or a packet of light. That's our smallest little piece, would be a photon. And the energy of a photon of light is directly proportional to its frequency. So when frequency increases, energy increases. So high frequency, high energy, low frequency, low energy. This is also inversely proportional to wavelength, the frequency is. And we've got a proportionality constant called Planck's constant, which has the symbol H. Has this value. I'll give you Planck's constant and the speed of light on exams if you need it. But this is 6.626 times 10 to the minus 34, which is the most extreme exponent for scientific notation I think that we'll see in the class. Minus 34 is crazy, crazy small. And we've got these two equations that we can use with it. I was too busy grading, so I didn't cover up all the answers, so they're just in here with us. We've got a problem. A 100-watt light bulb radiates energy at a rate of 100 joules per second. The watt is defined as 1 joule per second. If all of the light emitted has a wavelength of 525 nanometers, how many photons are emitted per second? So we've got 100-watt bulb. We're getting 100 joules per second. The wavelength is 525 nanometers. We want to know how many photons per second. We've got some equations. Energy equals Planck's constant times the frequency. We also have that the energy is equal to Planck's constant times the speed of light over lambda. And H is 6.626 times 10 to the minus 34 joules seconds. Okay, these are both basically the same equation. We can't use the left one because we don't have we don't have the frequency. We're going to use the right one where nu equals c over lambda. So we've substituted in for nu, c over lambda. That's how we got the equation here on the right. We would also need to remember that c, or look up, that c is equal to 3 times 10 to the 8 meters per second. And this E is the energy of 1 photon. It's going to be a really small number. So our energy is equal to Planck's constant in joules seconds times the speed of light in meters per second. These seconds will cancel out, and that's going to be over our wavelength in meters. Remember that nano equals 10 to the minus 9. So if we don't want to really do any math, 525, we substitute in the 10 to the minus 9. This wouldn't be correct scientific notation, but our calculator will still understand it, and it will give us the correct answer. The meters will cancel, and this will give us an amount in joules. That amount in joules is going to be 3.786 ... times 10 to the minus 19 joules. And now we get to use the joules per second, 100 joules per second. This is the total amount of energy per second. This is the energy of 1 photon, so how many photons does it take to equal this many joules? If we put joules per photon, then that might help us see how we can find it. We take the 100 joules per second, we divide it by the joules per photon. That's multiplying. I'm going to flip that to the bottom. Whoop. And this will tell us the photons per second. It's going to be the 2.64 times 10 to the 20 photons. I'm 90% sure I did not give one of these questions on an exam last semester. I probably won't again this semester. It might show up as a multiple choice, if anything. All right, practice with arranging the 3 colors of visible light, green, red, and blue, in order of increasing wavelength. So shortest wavelength to longest wavelength, frequency, shortest frequency to longest frequency, energy per photon, lowest energy to highest energy. You can come up with those 3. So we just talked through the order is going to be the same as rainbow. This is why I like that rainbow trick that I showed us earlier. I think that's a fun memory device for this. So just drawing in the 3 colors that we have, they're going to show up in this order in a rainbow. If we stretch those lines out, if we flatten these lines out, the length of the lines corresponds to the wavelength. So red is going to be the longest. Blue would be the shortest. So for wavelength, it's going to be blue. then green, then red, because red's the longest. How does frequency play into this? How is frequency related to wavelength? Are they the same order? Are they the opposite order? Is it some weird mashup? It's the opposite order. So red's going to be the lowest because it's the longest. Green will be the middlest again. And blue will be the highest frequency. And then what about the energy per photon? How is that going to relate to frequency? Is it going to be the same order, the opposite order, or some weird mashup? It's going to be the same order. The other way we remember for energy per photon, there's two types of light on the electromagnetic spectrum that have visible light colors in them, infrared and ultraviolet. What does ultraviolet light do to you if you get too much of it? Skin cancer, sunburn. Infrared will not do that. You can get exposed to lots of infrared. It's not going to give you skin cancer or sunburns. So ultraviolet, violet is next to blue after indigo. Blue is going to be the highest energy. So it's going to be the same order. Blue is near violet. UV is next to violet. UV gives you sunburns if you get too much of it, and depending on what sort of genetics you have. If I asked you a question on an exam and I said, what's the longest, shortest, most, least, greatest, smallest of any of the properties for light, what's a color that you should never pick? It's never going to be the shortest, it's never going to be the longest of these three. Green. Green is always in the middle. You would never pick green if these are your three options. So in a superlative question, in a least, most, biggest type color question, never pick an inside color. You want to pick whatever's closest to red or red. You want to just a test-taking strategy. So if you get one of these questions on the exam, you will get one of them on the exam. Make sure that you don't pick an inside color. Never pick green or orange if red is on there, for example. Okay, going back to our photoelectric effect. We're shooting light at metal. It's hitting the metal is ejecting electrons. We learned that there is a threshold frequency. One photon at the threshold frequency has just enough energy to dislodge one electron. Is the binding energy of the electron, the amount of energy that the electron is stuck to the metal. How much energy it takes to break off the electron. That's this Greek letter phi. If you have a higher frequency photon, the electron will absorb more energy than is necessary to escape. So if you hit it with just the right amount of light, the electron breaks off and it's got barely any energy. If you hit it with more, electron. So it becomes the kinetic energy. So the kinetic energy of that ejected photon, or the ejected electron, is h nu, the energy of the photon, we just swapped that in, minus whatever amount of energy it was holding on to with, which is the Greek letter phi. The energy of the photon, energy to break, to eject, let's say, electron from the metal. So thinking about this conceptually, not putting numbers to it, we can do calculations with numbers to it. I'm guessing that you probably have some of those on Alex. Suppose a metal will eject electrons when it's struck with yellow light. What will happen if the surface is struck with ultraviolet light? So the threshold is yellow light. We are hitting it with ultraviolet light. Is it that no electrons are going to be ejected? Is it going to be electrons will be ejected, but they'd have the same energy as those ejected by yellow light? They'll be ejected, they'll have more energy than if they were hit by yellow light. They'll be ejected, but they'll have less energy than yellow light. So what we should be thinking about with this problem, the threshold is yellow light. So the minimum to eject is yellow light. It's getting hit with ultraviolet light. How do those compare to each other? How does ultraviolet light compare to yellow light? Does it have more energy, the same energy, less energy, something entirely different? Ultraviolet has more energy. So we're thinking, which has more energy? And the answer would be UV has more energy. So is UV light going to be able to eject electrons? Cause electrons to be ejected from the metal if it has more energy? Yes, no, something else? Yes, it can cause electrons to be ejected. So A is wrong. Are the electrons going to have the same, more, or less energy versus if they got hit by yellow light? This is where this equation can be helpful. So the binding energy would be yellow light. We're hitting it with UV light. UV light has more energy than yellow light. There's going to be extra kinetic energy. So the difference between UV and yellow, the energy difference, will go into the ejected electrons. So more kinetic energy. They're getting hit with more energy. That energy has to go somewhere. It goes into the electron. The electron takes it with it as it's ejected from the metal. Any questions at all? We haven't really gotten to the quantum mechanics stuff yet, but we should hit some of that yeah, we'll hit some of that next class. So we'll stop for now.